So the easiest way to think about it is you have real-world signals out there in the world that you might want to measure, like my voice, for instance, music, various videos, and then some instrumentation kinds of things like sensing vibrations in the ground or a variety of things that you want to sense. Those are all in the analog domain, meaning that they're continuous, the signal's continuous. And the real advantage of digitization is you can basically have arbitrary accuracy. You can digitize as large a number of bits as you can. It may cost more money. The converter may be more expensive, but in principle you can digitize very accurately. That's one advantage, and the second one is one that you'd mentioned before about these JPEGs and MPEGs and so on, or MP3, which is the audio format for compression of audio signals. You can't compress an analog signal. It has to come out in order and it has to follow in time. So you can't reinvert bits and do things like that. But with digital, you don't really care. You can reorder the bits and do anything as long as you want, at the time you're playing it or putting it through the speaker, you put it back in the order you want. And that's what gives you, that's a very powerful issue that you have with digital technology. And I think the most interesting thing about analog to digital conversion is that there are a variety of signals in the world. Some are pretty slow, like for instance, I mentioned something about measuring seismic signals or vibrations in the earth. They can be on the order of 10 to 20 cycles per second. Some are very fast. Video signals, for instance, you end up having to digitize quite quickly. And so what you have is a variety of requirements on analog to digital conversion that span two axes. One is speed, how fast it goes, and one is resolution, or how accurate you want to digitize the signal. And of course, to get both of those is the hardest, and usually what you have is architectures that either work best slowly but very accurately, or fast and not so accurately. So the way a successive approximation A to D converter works is you take your analog signal and you break this 0 to VREF, you break that up into steps. So we say, okay, my first question is it larger than halfway or smaller than halfway? And if it's larger than halfway, I say it's a 1. If it's less than halfway, I say it's a 0. Now let's suppose it was larger than halfway, or on that diagram we're traversing up the tree there. Our first bit is a 1, and then we go and we check, is it greater than 3/4 or less than 3/4? And if it's greater than 3/4, we'd go up the tree again, and that would be 1, 1. And then we go up, we check again, we say, okay, well now is it greater than 7/8 or less than 7/8? Now let's suppose it's less than 7/8. Then we'd go down the tree on that last branch, and my output would be 1, 1, 0, which would represent an approximation to that analog signal. So successive approximation does steps, or tries to find the answer by stepping in units of a half, I guess I would say. So we talked about a serial converter which counted, and the other extreme from serial is to do something all in parallel. So instead of taking our reference and taking a step and the next step and the next step and the next step, let's present all of the possible references to comparators. And so on this picture you see that we have comparators, or a large number of comparators. Maybe if it's an 8-bit converter, we'd have 256 comparators. And we have a reference input to each one of those comparators. And the reference input then is different for each one of those comparators. We take our analog signal and apply it to every one of those comparators, and we see which ones trip and which ones don't. Now we build this in a particular way that the highest reference voltage is at the top of that diagram, and the lowest reference voltage that we're going to compare against is at the bottom of the diagram. So if your analog signal was somewhere in between, all the comparators at the bottom would have tripped, and then all the comparators above your analog signal would not trip. So one of the questions is how many bits do you really need to represent a particular signal? And I think pictures are the easiest way to understand this. And what we call the number of bits that you're going to use to represent that signal is the dynamic range. So the dynamic range is going to say how many bits are we going to have. So a 16-bit converter has about 65,000 possible levels. A 10-bit converter has 1,024 levels. An 8-bit converter has 256 levels. A 16-bit converter has a wider dynamic range than a 8-bit converter, let's say. If we take a look at the picture on the left and you see the shadow there where the ball is, that's a dark spot in the picture. And yet there are some very bright spots in the picture because this is sun reflecting on the sand, and what you'd like to do is be able to image or to have a representation in bits of both the dark signal and the bright signal. And so if your picture has very dark spots and very bright spots, then you need a wider and wider dynamic range. And so this is a shot where we had used a lower dynamic range camera on the picture on the left and a higher dynamic range or a wider dynamic range with the picture on the right. And you can see that you are able to represent the scene on the beach a little more real. So this is another picture just to show that, you know, the use of wide dynamic range, or to have this large range in conversion. And this is a picture of some automobiles or doing cameras for intelligent vehicles. And as you know, that we might have some sunlight shining when you're trying to see a car that's behind the first car here. And so the picture on the left, you kind of can't see the car that's behind because you don't have enough dynamic range. In other words, your signal's saturated at the top. Or if you had, say, just 12 bits and you saturate it at the top, you don't have enough dynamic range. What we'd like to do is to extend that width and have finer resolution, and that's what you see out of the second picture, so that you can see the car in the back.
So this is a picture of a project that we're involved in right now, which is a sensor network that would be deployed in a forest field. And what you'll see is those black dots represent sensors that are dispersed throughout this ravine. And then those three sticks that you can see coming up are actually towers that have sensors along the tower. And so each of those sensors can actually measure temperature, and then those are all communicated back to the main source, which is at each of those towers. So this is something that we plan to actually deploy in a real forest environment. And the reason that we want to take temperature measurements is we want to determine the airflow. And the airflow tells you about things like contaminants and how they might propagate through a system, or it can also tell you about things about global warming. So it's really important to be able to study those environmental factors. So if we now look at those sensors, and we go to the next slide, this shows kind of a very general block diagram. And what you'll see here is that there's a few A to D converters that are included. There's an A to D and a D to A converter that are part of the transceiver. So there's going to be a wireless transmission where we communicate with the hub, the central hub. And there's an A to D conversion that occurs there. Typically it'll be about 6 to 7 bits for that kind of wireless conversion. And then there's also an A to D converter that has to interface to the sensor. In this case, we have a temperature sensor. And so just to illustrate how we might use this A to D, or how we figure out what's important about that A to D, in this case we want to measure temperature of about a 40 C range, and with resolution about plus or minus 0.5%. So if we take that, we have approximately 100 steps. It's really about 80, but we'll round it up to 100. And if we then back annotate that, that turns out to be about 40 dB of resolution, or in this case about an 8-bit A to D converter is needed for this sensor.
And what we're plotting here is a figure of merit that takes into account both the dynamic range and the speed. And this figure of merit is calculated by multiplying some number that represents the dynamic range. That would be 2 to the n, where n is the number of bits. The bandwidth, which is the speed at which we sample the signal, that might be 1,000 times per second or 1 million times per second. And then we throw in one other factor, which is power dissipation. And since data converters we want to have, they're pervasive. They're in a lot of our consumer electronics equipment, such as digital cameras or Palm Pilots, all kinds of different things where we're doing data conversion. We want to have the power dissipation low so we don't have to change the batteries all the time. So the figure of merit is the dynamic range times the bandwidth divided by the power dissipation. And what's plotted here is this figure of merit for a variety of reported A to D converters versus time, or versus the year they were reported. So we're plotting here the time on the x-axis from about 1973 out to about 2003, where the data was taken. And you can see there's a lot of variation in what the reported papers are in terms of this figure of merit. But you can generally say the trend is going up, meaning we are increasing the amount of resolution we can have, the speed it can run, and doing it at a lower power dissipation as the technologies advance.